Hello and welcome. Today, I'll be showing you engineering concepts through simple experiments involving commonly found household items. Capillary action is what makes this pen's ink reservoir go down to the nib. Scientifically, it's described as the ability of a fluid or liquid to flow from point A to point B without additional assistance. The materials you need for this project are 2 paper towels, 1 paper towel to clean off your spoons, 3 cups, blue food coloring, yellow food coloring, 2 spoons, and some water. First, we're going to begin by pouring the water into both of these cups. Make sure to pour half and less the actual water level of the cup, and try to pour an equal amount into both of the cups. Alright, now we're going to take the blue food coloring first and add about 4 drops. After we add our food coloring, we'll take our spoon and stir it up so we get a nice rich dark blue. Then we're going to take this cloth and set our spoon aside for now. We'll do the same with the yellow dye, adding about 4 drops. And then we'll stir well, just like we did with blue. Alright, setting both spoons aside, let's now focus on these paper towels. We'll take each paper towel and we'll fold them into 4. First half and then lengthwise, so that we'll have a nice long strip of paper towel. Then we'll put one end directly into the yellow, one into the empty cup, and do the same with the blue. Alright, now let this sit overnight and watch what happens. Update number 2. After a full 24 hours, we can see clearly that there's green liquid in this middle cup, with the water level here rising, and the water levels in these 2 cups, the blue and yellow, lowering. If we leave this for a few more hours or a few more days, what's most likely to happen is that the water level here will rise to equal the water level in these 2 other cups. That is to say, the water level in all 3 cups will become equal. This experiment requires patience, but it's really rewarding to watch it happen, isn't it? The capillary action in water has allowed for the water to rise up through these paper towels into this green cup. Essentially what we've done is fill this cup without pouring a drop. Thank you. Have you ever ridden on a carousel before? A carousel uses hydraulics, which is the branch of technology associated with the mechanical properties of liquids. For this experiment, you'll need the same 1 foot of polyurethane tubing, 2 syringes, and an amount of water. What we're going to do first is open one of these syringes and fill it with water. Then, we're going to do the same thing that we did for the pneumatics experiment. Remember to screw the syringes as you try to insert them into the tubing. As you can see here, we see many of the same results. One difference that you might note between hydraulics and pneumatics is that liquids are not as easily compressed as gases. With the pneumatics experiment, you may have noticed that the volume of gas occupied changed a little each time. That when you press down on one end of it, the other end would not go as far up. Liquids, however, are less compressible than the air was, and so you see the same volume approximately each time. This concludes this experiment. Centrifugal pumps are used in sewage, water, and petroleum pumps across the world. Today, I'll be showing you how to make your very own centrifugal pump. What you'll need for this is a supply of water, a little bit of duct tape, a straw, a skewer, a pair of scissors, and a ruler. This straw was approximately 9 inches, so I measured and put a mark at 4.5 inches, 3 inches, and 6 inches. Then what you want to do is you want to take your skewer and insert it at the middle marking, which was 4.5 inches. After you've pierced the straw and inserted the skewer a ways, you want to take your pair of scissors and cut at both the flat 6-inch marking and the 3-inch marking. But you want to do this without cutting all the way through the straw. There should be a little bit of space between the straw that isn't cut, like so. Setting the scissors aside, we can see that we can make a clear triangle like so here. Now what we want to do is lay the duct tape like this, and then put the skewer right on top. Then we'll gently fold the pieces of duct tape over the straw, like so. Using the other piece of duct tape, we'll do the same thing we did to the bottom on the top. Alright, now let's go outside to test this. Alright, let's see how well our centrifugal pump works. As you can see from that demonstration, the rotational kinetic energy converts into hydrodynamic energy as the water shoots out these two streams. Let's see that again. And now you know why we came outside. This concludes this portion of the experiment. This experiment is intended to show you how a liquid can alter the magnetic properties of a paperclip. For this experiment, you'll need 3 clear cups, preferably, and a set of paper clips. For this, we have about 4 paper clips in each cup. We also have honey, canola oil, and water as our choice of liquids. And we have 2 stacks of magnets, plain refrigerator magnets. Let's see how magnets attract the paperclip without any liquid first. As you can see, at first the paperclips moved slowly towards the magnet, and as the magnet got closer, the rate at which they moved at increased exponentially. Let's start off with water. Alright, be sure to compare this to how the clear cup with no liquids worked. As you can see, when there was no liquid in the cup, the paperclips moved quickly towards the magnet. But after we added water, there was less of a force between the magnet and the paperclip. This is because water is diamagnetic, which means it has a weak repulsive force. It causes a weak repulsive attraction to be between the paperclip and the magnet. Now for canola oil. As you can see there, the paperclips in oil moved a lot faster than they did in the water, but they still weren't as attracted as they were when we had a clear cup with no liquid. Now for honey. As you can see, here the paperclips moved very slowly, even slower than they did in water. Water and honey are both diamagnetic, whereas oil is paramagnetic. Paramagnetic is essentially opposite of diamagnetic. You can also think of this in terms of densities. Water is in the middle, honey is the most dense, and oil is the least dense. Thank you. Alright, let's look at these again to give you a better perspective. Here we have our three glasses ordered by density, honey, water, and oil respectively. And the magnets. Each glass has one paperclip that's roughly in the center. Let's start with the oil. As you can see with the oil, the magnet had to get fairly close enough to the glass in order for the paperclip to move. As you can see with the water, which is also diamagnetic, when I put the paperclip there and the magnet here, the paperclip almost didn't move at all. When I brought it over here and there was less of a distance between the paperclip and the magnet, it did move. And now for the honey. As you can see, in honey, the magnet and the paperclip must be a much closer distance than it does need to be in water. And in oil, we can pretty much attract the paperclip from anywhere. This concludes this portion of the experiment. Why are we in the bathroom, you ask? Well, today I'm going to teach you how to bend water. No, not like Katara from The Last Airbender, but with this comb and this towel. First, you're going to open a steady stream of water. For this, I'm going to use cold water, and it's going to be a very thin stream so that you can clearly see what's happening. You can also use a PVC pipe instead of the comb, or a plastic tube like shown here. The report card folder and duct tape are just so that you can see the effects a little more clearly. What you're going to do is take your item, place it between the towel, and rub it vigorously for a few seconds. As you can see, this uses electrostatics, which is removing the charge from the comb, taking it to the towel, so that the comb is charged enough to pull the water one way or the other. Electrostatics is a very common principle of physics that's used in things like defibrillators, photocopiers, as well as laser printers. This concludes this portion of the experiment. From our dams to our flush toilets, siphons are present and ever useful in our everyday lives. For this experiment, you'll need a height, 2 containers, one filled with water, and polyurethane tubing. First, we're going to take this container of water and place it on top of this basket to give it a higher pressure. Water, under the influence of gravity, will always flow from a region of higher pressure to a region of lower pressure. Now, unwrapping this polyurethane tubing, we'll place one end in the water container, like so. And then we'll take the other end and place it to our lips. After sucking a little bit on this polyurethane tubing, we'll place it into this water container and watch what happens. As you can see, water is flowing from this region of higher pressure to this region of lower pressure. Siphons do need to be primed, and that's why we usually suck on the water tube before we place it in this region. The water flow is getting slower mostly because this tube is almost at this region, which means it won't be connected to the water anymore. Now we can take the tube out. Let's make sure it's empty. And there you have it. Water flowing from a region of higher pressure here, because the water is at a height, to a lower pressure here, via the use of polyurethane tubing. This concludes this experiment. Let's come back to the concept of weight distribution. Here, I have a single sheet of paper cut in half. One side is plain and the other half is accordion folded. Here you can see 3 paper cups and a handful of pennies. Let's take these paper cups and put 2 of them down. After that, we can put this plain sheet of paper on top and then have this paper cup in between them. As you can see, the bridge is holding, but it doesn't seem all that stable. Let's try putting pennies into this cup and see how long the bridge can last. 1. As you can see, this plain paper bridge isn't strong enough to hold even 1 penny. Let's try the accordion fold and see how much better it does. Ready? 1. Let's just center this cup. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 pennies. Much more than the plain sheet of paper could hold. As you can see, these ridges are much better at distributing the weight of the pennies across these 2 cups, which makes this bridge more effective than this plain paper bridge. This concludes this experiment. Let's do another exciting demonstration involving distribution of weight principles. For this one, you'll need blocks and some craft sticks. Take 1 block and place it in the center, and then put 1 craft stick on top of it. Make sure that the craft stick is centered upon the block. Then, select 3 additional blocks, place 1 in the center, just above the first block you placed down, and then place 2 blocks equidistant from the center. Then, top the tower off with another craft stick, and do the same, selecting 3 additional blocks and placing them in the same positions. As you can see here, that 1 block at the bottom is now holding 6 colored blocks. This makes 9, 12 blocks so far. Now we have 15. And 18 blocks. As you can see, distribution of weight is truly amazing, as that 1 little block at the bottom is now holding 18 of these same size blocks. This concludes this experiment. Ever watched a movie and seen the Golden Gate Bridge come up? All bridges use the concept of distribution of weight. For this experiment, you're going to need a stack of paper cups, and 2 cut pieces of cardboard that are about the same size. First, stack the paper cups in rows of 3, having them be approximately the same distance apart. You can see here that we've used 12 cups, each in rows of 3, which makes 4 rows total. Now to test this out, I'll ask my volunteer, who is 59 pounds. Suspense is killing me. Will the bridge hold? And there you have it. A simple 12 paper cups can manage to hold 58 pounds through distribution of weight. Each of the cups takes a portion of my volunteer's weight and distributes it across the cups, so that no one cup has enough weight upon it to crush the cup and break. This concludes this experiment. We might not have the materials to build a futuristic hovercraft, but we can at least make a pretty simple one. For this experiment, you'll need a balloon, a dishwashing liquid bottle cap, or a push-up water bottle cap, an old used disc, and some super glue. First, what you're going to do is take the super glue and you're going to glue the bottle cap onto your used disc. Alright, let's wait for the glue to set and come back to finish the experiment. Here's an update on our hovercraft. As you can see, the glue between the dishwasher bottle cap and the CD is clearly set. I've also added some duct tape around the edges for added stability. Watch what happens when I open the dishwasher cap. Let's watch that again. Are you ready? As the air is released through the dishwasher cap and the hole in the CD, a region of lower pressure is generated. Underneath the air cushion generated is a region of higher pressure, and therefore the hovercraft is able to glide along a smooth surface. This concludes this experiment. This project is designed to show you polymer behavior. What are polymers? Polymers are long chains of many molecules. Polymer engineering is most commonly used in aerospace, automobiles, as well as in mundane applications such as fishing line and bicycle tires. For this experiment, you'll need a plastic bag, a supply of water, and a few sharp, round pencils. Be sure not to use pencils that have ridges or are in hexagon shapes. Save these for your standardized test kits. First, we're going to open the plastic bag, and we're going to pour water into it. If you don't want to get messy, you can use a clear plastic tub like I have here, or you can use a bucket or some other holding container. What we're going to do is poke a sharp pencil straight through this bag, like so. Then we'll take another one and do the same. As you can see here, the bag has two pencils straight through it, and it does not leak any water from it. Polymers have sufficiently sealed around these pencils so that the bag does not leak any water. This is just one of the many useful properties of polymers and why they're used in so many different things. Now, as I remove the pencils, you can see that the holes made by these are permanent, and so that the bag will leak if the pencils are removed. This concludes this experiment.